All right, hello everyone, and welcome to another very entertaining video. Today's topic is on lipids. We continue to apply what we learned about chemistry to build stuff, to build these macromolecules. We've talked about carbohydrates. We're going to talk about proteins. Today, the focus is on lipids. And what we have here listed the three classes that we're going to discuss. When we think about lipids, we commonly think about fats, and we think, they're not healthy, whatever. I want to make sure that we understand, first of all, what these three classes are and why they're so important. So, as you can see down here, our task, let's build these molecules. We've talked about functional groups. We want to be able to see how these things glue together. And then by looking at the structure, we want to be able to understand and predict behavior. So as we think about building them, the two questions that I've got listed down there, what are our building blocks for each molecule? And what are the bond types and how are they formed? So let's start first with triglycerides. Triglyceride, as the name implies, we've got a couple of things. We got tri, meaning three, and then we've got this glycer part. This refers to glycerol backbone. So we've got one glycerol backbone, and then we've got three of something, and those three tend to be three fatty acids. And so before we proceed any further, we need to understand what a fatty acid is and why this is a building block for these triglycerides. The functional group of the fatty acid is a carboxyl group, which, if you recall from our video on functional groups, has a superpower as an acid. It is a proton donor, and it looks like this. And if you recall from that video, the R is just random, whatever, right? We're going to continue that in just a second. But it's the C and then the two oxygens. Because both of those oxygens carry so much electronegativity, so much pulling power on those electrons, the hydrogen often can leave, and at physiological pH often does leave as H+. And so you might see this drawn without the H there, but simply an O negative because it's donated that proton. And this is the idea behind what a carboxyl group is. That's why it's called an acid. Now, the fatty part is a hydrocarbon chain. And if we think about this is a lot of carbons and hydrogens, which are nonpolar covalent bonds. This is why triglycerides don't readily dissolve in water, simply because there's not a lot for water to bind to. So let's expand this. For simplicity's sake, we'll make this 10 carbons long. Fatty acids tend to be even numbered because they're usually built in 2 carbon subunits called acyl groups or acetyl groups. And so this one, 10, fits. Most in the body, 16, 18, palmitic acid, things like that are a little bit longer, but they're varying sizes. Of course, this is going to be covered with hydrogen. And because we know that carbon makes 4 bonds, all of these are hydrogens. We'll draw a few here. We don't need to draw them all. Now, this brings up a key point because when we think about fatty acids, there's a couple of different things to think about. First of all, saturated versus unsaturated, and what that actually means. So when we think about saturation, a sponge gets saturated. Ooh, a diaper is saturated, right? That just makes you cringe. Why? Because you know it's full of something. It's saturated with something. Here, what am I saturated with? I am saturated with hydrogens. And indeed, what we've drawn up here is a saturated fatty acid. Now you might be questioning, well, how is that ever going to change? How could it be unsaturated? Well, what would happen if we came in and put a double bond, so an extra bond right there? Now we've got a carbon-carbon double bond in the primary carbon chain. Both of those carbons, this carbon and this carbon, are now making 5 bonds each, and that doesn't work. We know that carbon makes 4 bonds. So, hydrogens get kicked off. This hydrogen has to leave. This hydrogen has to leave. And we're left with a molecule that looks like this. This is an unsaturated fatty acid. So, by default, let me state this again. if it's an unsaturated fatty acid, I know that there is a carbon-carbon double bond in the primary chain. Of course, you might be thinking, well, why do I care about that? Well, this is important because the vast majority of naturally occurring unsaturated fatty acids are cis fatty acids. But the next thing we want to talk about when we think of unsaturated, we have to think of cis versus trans. Back in the 80s and 90s, trans fats were a big deal. Nobody really cared about them. We realized near the turn of the century that trans fats aren't healthy. They actually cause significant problems because the body doesn't know what to do with them because they're kind of artificial. And so they would just build up in the body, and then if your body couldn't get rid of them, then it would cause cardiovascular disease and lead to heart problems. And this was actually killing people. So trans fats should be avoided really at all costs because the body doesn't really know how to process them. I'm not saying all trans fats are bad. Your body actually makes some trans fats, but commercial trans fats are generally speaking not good for you. And when you hear the term trans fat, that's what it's referring to. It's referring to a commercial trans fat. So what we really want to focus on is this idea of cis. Now, just to make sure, the fat that we've drawn up above, this is a cis fat. How do I know? Cis means the same, trans means across. The fact that we're missing two hydrogens on the same side, this is how I know it's a cis. If we had removed this hydrogen instead, and we have one down here, right? Now we can see that the hydrogens that came off are across from each other, across that double bond. This would be a trans fat. Why is it important that we know the difference between these? Well, let's go back to the cis fat, and let's maybe draw in a different way. We know that these carbon-carbon double bonds and the carbon-hydrogen bonds, they're not coming off of the carbon at a 90-degree angle like we've drawn it. Rather, they tend to be more like this. So let's draw a carbon-carbon chain. This is a little bit more realistic. And of course, the hydrogens will be coming off in this direction and in that direction into the screen and out of the screen as we try and apply some three-dimensionality to this. These will be our hydrogens here. Okay, now we can see the value of understanding cis versus trans. Let's come over here to this middle carbon and let's put these hydrogens back on. If this double bond is a trans double bond, we see that we're coming into the bond from the bottom and we're leaving the carbon bond from the top. A trans fat maintains the overall linear shape of this molecule. But if it's a cis fat, we come in on the bottom and we actually leave on the bottom. So what we need to do is reorient the rest of these carbons. And we have something like that, where we actually put a bend or a kink in the carbon chain. Now instead of linear, we come down and we bend. So cis fats have a kink, whereas trans fats remain linear. And this is actually very, very, very important for reasons that I'll show you right now. But first, let's go back and let's understand what the triglyceride is. Now that we understand this, what a fatty acid is, let's build a triglyceride, and then we'll show you why cis and trans fats, why cis fats are important and how they regulate the behavior of these structures. So we've got fatty acids. We know what those look like. We now need a glycerol backbone. Glycerol is just a 3-carbon alcohol. So let's come down here and let's build it. We have our 3-carbon alcohol. And you'll recognize that these are hydroxyl groups or alcohol groups from our functional groups lecture. And we're going to add that to the fatty acid using the carboxyl group as our reactive group. So there's our 10-carbon fatty acid. We talked about dehydration synthesis. This is the same thing, right? It's another example of dehydration synthesis where we see water right there. Water is going to leave, and as we remove H2O, we're going to remove that structure right there, and that fatty acid slides over, and now we've got a direct link between what was the hydroxyl group and now the hydrocarbon chain of this fatty acid. This structure that we see where we've got the carbon, then the oxygen, then a carbon double bonded to an oxygen, and then the rest of the chain, this is called an ester linkage. And to complete the triglyceride, all we have to do is do that 2 more times. Now we have our triglyceride. The one thing that I want to recognize is because these are all hydrocarbon chains, they're very hydrophobic. Remember, water likes polar charged things. These are nonpolar and therefore don't have inherent partial charge to them, so water really has nothing to bind to. They're happy hanging out together. And if they're linear, in other words, if they're saturated is linear, like trans, but trans is kind of a thing of a bygone era. If they're saturated, they're linear. And if they're linear, they can pack together very, very tightly. But what happens if one of these is a trans? Let's take this bottom one, for example, and let's put a kink in it. Because the cis bond makes a bend in the hydrocarbon chain, this expands the overall size of the molecule. So when we're thinking about cis, right, it's going to be less dense, and because of that, the interactions holding all these things together are fewer. So this type of fat, these tend to be liquid at room temperature. This is essentially the difference between, say, butter or lard, which is an animal fat and therefore saturated, which is for the most part solid at room temperature, versus canola oil or olive oil, vegetable oils that are liquid at room temperature because they're full of unsaturated cis fats. All right, so the triglyceride, this is what we think of when we think of fat. It's important in the body for insulation, for cushioning, and for energy storage. There's a lot of energy. As we talk about metabolism in a few units, there's a lot of energy stored in these molecules, and that's why we use it as a long-term energy storage molecule. All right, next on the list, phospholipids. To build these, we're going to continue exactly like we did with the triglyceride. In fact, turning a triglyceride into a phospholipid is not hard to do at all. So we go back to our glycerol backbone. There's our glycerol backbone, and we add our fatty acid to it through an ester linkage. We'll do that for all 3 of them. Okay, now we've got a triglyceride. To make a phospholipid, we're going to change it up a little bit, and we're going to cut off this bottom fatty acid. There we go, it's gone. And instead, what we're going to bind to through a phosphoester linkage, we're going to bind to a phosphate group. This is going to be P, it's going to be double bonded to an oxygen, and then OH and OH. We talked about this also being acidic. It's an important functional group. But importantly, the one thing that I want you to recognize really quickly, remember, this hydrocarbon chain is very hydrophobic. This phosphate group is actually often bound to a very hydrophilic structure, one of many different types that we would just call a polar head group. I don't know that that's super important. The phosphate is important. But I want you to recognize, if this is hydrophobic, this hydrocarbon fatty acid, and then look at the phosphate group, and then this polar head group, this is going to be very hydrophilic. And so what happens? Well, these 2 parts of the molecule, they don't like each other very much. They kind of repel each other. Some of it likes water, some of it hates water. So what we're going to see is around this axis, we're going to rotate so that this phosphate group gets as far away from this end of the molecule as possible. So let's move everything over. And now we have a phospholipid. It's the same glycerol backbone, 2 fatty acid tails, and then a phosphate group, often bound to any one of lots of different types of polar head groups. We're not showing that right here, but that's okay. I want you to recognize we're hydrophobic here, we're hydrophilic here, and this creates a unique attribute where across the molecule we have both hydrophobic and hydrophilic domains. The term we use to describe this type of molecule is amphipathic. Again, amphipathic just means I'm hydrophobic on one side, I'm hydrophilic on the other side, and we want to take just a second to appreciate what that looks like. If I take a bunch of phospholipids, I got them in my pocket, and I throw them in a puddle of water, what will they do spontaneously? Well, if I've got one side that hates water and another side that loves water, I hope you can appreciate that these things will, just to conserve energy, randomly orient themselves so that the hydrophilic part is pointing out toward the water and the hydrophobic parts come together to form a core. And we could see that in the formation of what's called a micelle, where here's my phosphate, my fatty acid tails, this is how you often see them drawn, and they would form all by themselves. There's no glue holding these things together, but they're going to form a sphere, and all the fatty acid tails point to the inside. Out here, right, I love water, H2O, smiley face. I love water, but on the inside, no way, right? That stuff hates water. Well, these micelles provide really great carriers of fats, and in fact, this is how we carry things through the blood. When we think of structures like LDLs, low-density lipoproteins, or HDLs, high-density lipoproteins, you may have heard these as the bad cholesterol and the good cholesterol. It's kind of a misnomer. Although cholesterol could be carried inside of these, because cholesterol is hydrophobic, I'm going to be carrying cholesterol in here. I'm going to be carrying triglycerides inside of it. There's going to be proteins on the surface. That's what makes these HDLs and LDLs different. But the essence of this molecule is the phospholipid that, because of its amphipathic nature, can exist in blood because the outside likes water, but it can carry fats on the inside and cholesterol, which would otherwise not like to be in the water. It's a great transport vessel. Where else do we see these phospholipids? Well, in bigger structures, this is what makes up our cell membrane. Every single cell in the body is made of what's called a lipid bilayer, and we'll talk more about this in the next unit. We'll just draw all those, and then another layer down here. We've got the phosphate groups, polar head groups, and then pointed toward the inside, we have all of our fatty acids. So this region right here is hydrophobic, but water can exist on both sides. So the outside, the extracellular matrix, is all water. The inside of the cell, the cytoplasm, it's water. But the membrane itself is hydrophobic. And this creates a really nice barrier. Right? Again, there's no glue holding these things together. They're only held together because they don't want to hang out with water. And this allows the cell to regulate what goes in and what goes out, because most things are hydrophilic. And so it's a really good way to regulate and provide protection to the cell. All right, the third class that we want to talk about, steroid lipids. We don't want to spend a lot of time talking about how to build these, mostly because the biochemistry is a headache. But if you saw one, I would want you to recognize it. So a steroid lipid is a 4 hydrocarbon ring structure. 3 of these rings are hexagons, and the 4th ring is a pentagon. This overall structure defines what a steroid lipid is. And by far, the most important steroid lipid you have in your body is cholesterol. Let's draw on some of the things that make cholesterol cholesterol. We've got a hydroxyl group there. We've got methyl groups here and here. And then probably most importantly, this big hydrocarbon chain sitting on top. That's really what makes it super hydrophobic. It doesn't like water at all. You need to throw a double bond in there. That's cholesterol. That's what it looks like. Cholesterol is essential for proper cell function. And if you're not eating enough cholesterol, your body can go through some biochemistry to make this stuff. The brain is probably the biggest storage area of cholesterol. Up to 20% of all cholesterol stores are happening or are up in the brain. Because of how important it is in maintaining cell structure. So it has two key purposes that we want to list. Number one, it acts as a fluidity buffer. What does that mean? Well, let's go back to the idea of cell membrane. We just drew one of those. Let's draw another one. Phospholipids with their fatty acid tails pointing inward. Maintaining the proper fluidity is important for the health of this membrane. Remember, there's no glue holding these phospholipids together. And also, if you think about the ratio between saturated and unsaturated fatty acids in here, you can appreciate we could be very dense like butter or very liquid like olive oil. I don't want to be too dense because that takes away my flexibility. But I don't want to be too liquid because that would just melt away, right? It would just dissolve. It would go all over. So I need enough solidity to keep together, but not so much that I become stiff and rigid. And that's where cholesterol comes in. Now, you can regulate these by temperature and things like that, but we are homeotherms. We regulate and maintain a constant body temperature, and so there are other ways to regulate fluidity. One of these is cholesterol, and the other is the length and the amount of cis double bonds in the fatty acid chains. Cholesterol is an important molecule that hangs out inside the cell membrane in between these fatty acid chains. And if the fatty acid tails start to get too far apart because it's too liquidy, cholesterol is there to grab them and pull them back together because it's super hydrophobic. Likewise, if they're starting to get too close together because it's too solid, cholesterol is a fairly large molecule and it sits in there and blocks them from becoming too close. It maintains distance. So it buffers fluidity at both ends of the spectrum, at both being solid and being too liquid. So that's the number one thing that cholesterol does. That's why it's so important in all of the membranes of our cells. The second thing that cholesterol is, this is a precursor for all steroid hormones. And I hope you were able to recognize this. If we're thinking about testosterone, estrogen, progesterone, cholesterol, aldosterone, all of these key steroid hormones, so important for bodily function, they're all based on this same four-ring structure. There's some things that I have to modify, right? I'm gonna certainly have to cut off that big hydrocarbon chain on the top. By removing that, it becomes a little bit more soluble in water so that these hormones can travel through the blood. There's other modifications, but they're all based on this same structure. So cholesterol is a precursor for all of the steroid hormones. So that wraps up steroid lipids, cholesterol being the most important. As we go back and review phospholipids, remember it's a glycerol backbone, two fatty acid tails, and then the phosphate group. And that sets up an amphipathic molecule where one side likes water and one side hates water, and that endows this molecule with some unique powers, able to make micelles that we talked about and be key components of the cell membrane. And then just a quick review of the triglyceride. This is going to be the same glycerol backbone, three fatty acid tails, and then understanding a fatty acid could be cis or trans, and that's going to be saturated versus unsaturated. All of that stuff that we reviewed contribute to our understanding of how these fats behave. And so we built the molecules, We understand the bond types, we understand how they're formed, and most importantly, we understand behaviors and the important roles that these three classes of lipids play in our body.